Good morning, dear students. My name is Ferhan Mazher, and right now I am with the 11th Cambridge class. And today is the 3rd of April 2021. My name is Ferhan Mazher, and the subject we are studying is Physics 5054. Today we have decided to do May June 2011 2-1 paper. This paper is a paper 2 theory paper which has structured questions. And in this session, we are going to solve its section B. So we'll be working only on section B. The section A we will solve in another session. So let's start this paper. And here we go. So on your screen, we have section B of May, June 2011 to 1. And question number 9 is in front of you. So here we have a diagram shown. We have a soft iron core, and on it we have a coil, and the coil is connected with a lamp. We have a bar magnet here, and that bar magnet is shown rotating in the anti-clockwise manner. So you see, when this bar magnet will rotate, electricity will be generated in the coil. The EMF will be induced, or current will be induced in the coil, and due to that, this lamp will lit. So why? Because when this magnet rotates, its magnetic flux passes through this coil, and because it's rotating, so the magnetic flux passing through this coil is changing. So due to this, you see the EMF is induced in this coil. We call it electromagnetic induction. So let's move to the question. The first question on your screen is, state how an alternating current differs from a direct current. So difference between an alternating or AC current and a direct current. The direct current flows only in one direction, whereas the alternating current flows in one direction and then in the opposite direction. In this direction, then in opposite direction. So, for example, if the current is flowing in the clockwise manner, then it will flow in the anti-clockwise manner. This is called the alternating currents. This is the main difference between the alternating current and the direct current, DC current. So I've written this answer on a paper. Let me show you my work. And here on your screen, direct current flows only in one direction, but alternating current flows in one direction and then the opposite direction, then in the opposite direction, or then in the reverse direction. So this is my answer. Let me check the marking scheme. The marking scheme says the DC current flows in one direction, or AC current flows in one direction, then the other. So very simple question, 1 mark question. Hope you will be able to do it. The next one is, explain in detail how alternating current is produced by the apparatus shown in the figure 9.1. So here an alternating current is produced. The reason is, you see this bar magnet is rotating. So if you put all your concentration on this left corner of this coil, so this north pole will approach. First of all, the north pole will approach, and when it will be rotating, the north pole will be approaching the coil. So the current will be induced in the coil, because the magnetic lines which are passing through this coil, they are changing because the north pole is approaching it. Then what will happen? Then the north pole, once cross this coil, it will move away from the coil. Then the current which will be induced, it will have a different direction. The current which will be induced when the north pole is approaching, it will have a different direction, and when the north pole is going away from this coil, the left side of the coil, then the current induced will have a different direction. So due to this, you see the current induced in the coil, it will have different direction. So let me show you my answer. I have written this answer also. It's a huge answer. Let me show you. So the north pole approaches left end of coil and then leaves. Then south pole will approach left end of coil and then leave. Magnet is moving relative to coil, so magnetic lines passing through coil are changing. EMF will be induced in the coil. Direction of the EMF will be different when the north pole approaches, and EMF direction will be different when the south pole approaches. left end of the coil. So I hope that you will be able to write this answer. Let's check the marking scheme. The marking scheme, let's see what the marking scheme says. It's a 4 marks question. And the marking scheme says that the mention of the there should be mention of the magnetic flux, magnetic field lines, flux cut changes in the coil. B1, 1 mark for the upper sentence, 1 mark for the second sentence. Induction of the voltage or current, 1 mark is for this. Something relevant, reverse, for example, field flux cuts in one direction, then other north pole approaches, then leaves. You can say this also, north pole approaches and south pole approaches, and like and link to the AC supply. So the current, when the north pole is approaching, the direction of the current produced will be different, and when the south pole is approaching the same end of the coil, the current induced will have a different direction. That's why the current which is induced in the coil will be alternating, because the direction of the current when the north pole is approaching will be different, and when the south pole is approaching that end, the EMF induced or current induced will have a different direction. It's a 4 mark question. Hopefully you have understood. The next one is state 2 ways in which the current in the lamp may be increased. If you want to increase the amount of current which is produced in this coil, there are several methods. So we have to mention there too. You can increase the number of turns per unit length here. Turns of the coil, the number of turns of the coil per unit length, you can increase that, the current will increase. Or use a stronger magnet, the current will increase. Or move or rotate this magnet faster, then even then the current induced its amount will increase. So let me show you my answer. I have written this answer also. So here you have to only suggest two answers. Increase the number of the turns of the coil or use a stronger magnet. I have written just two, and let me show you the marking scheme. What the marking scheme says: two any two of you can mention, thicker wires, more turns of coil, stronger magnet, faster rotation, lower resistance of the lamp. So you can mention any two from here. So the next question, let's move to the next part. And here we go. The generators at a power station produce a voltage of 25,000 volt. This voltage is stepped up to 400,000 volt by a transformer for long distance transmission on overhead power lines. The voltage is later stepped down to 240 volt. State and explain why the voltage is stepped up for long distance transmission. A 2 mark question and a very, very famous question, that why we step up the voltage before sending it in the transmission lines. The reason is we stepped up the voltage. When you increase the voltage with the help of the step up transformer, the amount of current decreases. And the power loss in the transmission lines is given by the formula P equals to I square R. So you see, when you reduce the amount of I, the power loss in the transmission lines decreases. So that's why we increase the voltage, so the current can decrease. And when the current decreases, the power loss in the transmission lines decreases. So let's check what I have written. I have written answer. Let me show you my answer. And here on your screen, the power loss in transmission lines is P equals to I square R. We cannot afford to change R. You can reduce the power loss by reducing the R value, but we cannot afford it. It's very expensive. By increasing the voltage by transformer, current decreases, so power loss in transmission lines is decreased. So according to this formula, when the amount of current I will decrease, and the power loss will decrease, and by increasing the voltage, the current is reduced. So that's why we increase the voltage, so that the current reduces, and by this the power loss in the transmission lines is decreased. So let's check the marking scheme. Marking scheme says to reduce heat or energy or power loss on the power lines. Higher voltage means lower current. For 1 mark for telling that the power loss will be reduced, and 1 mark is for telling that when the voltage will be high, the current will be low when you use the transformer. So next part, and the next question is calculate the ratio of the number of turns in the primary coil of the step-up transformer to the number of turns in its secondary coil. I want to find out the number of turns in the primary ratio, number of turns in the secondary. I know two things. You see here, I know the primary voltage is 25,000 and the secondary voltage is 400,000. So by using them, I can find out the ratio of the turns. So let me show you. I've done this on a paper, and the formula is very simple. Never forget this formula. The voltage in the primary divided by voltage in the secondary will be equals to the number of turns in the primary divided by number of turns in the secondary. The voltage in the primary is 25,000 and the voltage in the secondary is 400,000 equals to Np by Ns. So Np by Ns, if you do this on the calculator, 25,000 divided by 400,000 and write this answer in the ratio form, in the fraction form, on your calculator you will get 1 by 16. So the Np ratio Ns is equals to 1 ratio 16. 1 ratio 16. Let me check the marking scheme, and the marking scheme says 1 ratio 16. So our answer is right. I hope you have understood. Let's move to the next part. He says state one advantage and one disadvantage of using thicker wires in the overhead power lines. The transmission line, if you make them thick, what's the advantage? When you make them thick, their cross-sectional area increases, and when their cross-sectional area increases, their resistance decreases. When their resistance decreases, the power loss in them decreases. So the line losses decreases. If you use thicker wires in the power lines, overhead power lines, the power loss in them will decrease. There will be less line losses. What is the disadvantage? The disadvantage is when you use thicker wires, they become very expensive. One disadvantage, their cost is very high. Another disadvantage is that we call them pylons, the big towers which hold these lines. We call them pylons. And for thicker wires, you will need stronger pylons. So that will become very expensive. So I have written this answer also. Let me show you my answer. So you see the advantage is the thicker wires have lower resistance, so power loss will reduce. Disadvantages, the thicker wires cost more than thinner wires. Very simple answer. It's a 2-mark question. Let me read the marking scheme. The marking scheme says 1 mark is for telling that reduces resistance, less power loss, cost less to run, more current, more power. And disadvantages increase weight, more support needed, more wind resistance, more ice forms, costs more to install. So you can write the two, one advantage and one disadvantage easily. I hope you have understood. And let's move to the next part. He says, an electric drill power of 1000 watt. 1000 watt is used in a country where the main voltage is how much? The main voltage is 240 volt. State and explain the most appropriate fuse to use with this drill. So which fuse I should use? The power of the drill is given, the voltage is given. So first of all, I will calculate that how much current this drill will be taking. Power is equals to IV. So I will be equals to power divided by V. Power is 1000 watts, so divided with the 240 volt, you will get the amount of current. Then we will see that which rating of the fuse is good for this drill. I've done this on a paper. Let me show you my work. And here on the screen, you can see. Okay, so the power is 1000 watt, voltage is 240 volt. So power is equals to IV. I will be equals to power divided by voltage equals to 1000 watt divided by 240 volt. So the answer will be 4.17 ampere. You see the fuses which are given there. So the current the drill will take is 4.17 ampere. So the fuses which are given, I have to use that fuse whose rating is more than 4.17 ampere. So there is only one fuse whose rating is more than 4.17 ampere, and that is of 13 ampere. So I have to use 13 ampere fuse. If you use, there is only one fuse there whose rating is more than 4.17 ampere, and that's 13 ampere. So I have to use this. If I use any other fuse, and all other fuses which are given in the list, their rating is less than 4.17 ampere. So if I use them, so what will happen? The other fuses, if you use them, they will blow, they will melt, they will overheat, and obviously they cannot work. So let me show you the marking scheme. It was 1, 2, 3 marks. So we will have to choose 13 ampere fuse. And how we will came to know this? We will calculate the I value. That will be 4.17 ampere. And must choose higher value to avoid fuse blowing. If you use any other fuse which is not of which is less than 4.17 ampere, it will blow. It will overheat. So we can only use 13 ampere fuse here because we have certain number values given. Out of them, only the 13 ampere fuse is the best one, the right one to be used here. So it was a 3 mark question. I hope you will be able to write its answer. Okay, so here we go. We have okay, so here we have a 1500 ohm resistor is used on an electric circuit board in a television. Figure 10.1 shows the bands on a resistor, and the table of the figure 10.2 shows the color code for the band. So state the color of the bands on the 1500. So I will write 1500 as 15 into 10 raised to power 2. 15 into 10 raised to power 2. So for 1, I will use brown color. For 5, I will use green color. And 10 raised to power 2, for that 2, I will use red. Okay, so I've done this on a paper. Let me show you my work. You see, 1500 ohm means 15 multiplied 10 raised to power 2. So for number 1, I need brown color. And for number 5, I will need a green color. And 10 raised to power 2, for that I will need a red color. 2 is represented with the red. So the color coding will be brown, green, red. So and then he says a very famous question he's asking. He says determine the maximum value of the resistance that can be shown with this 3-band color code. You see, if I use white color, it mean 99 expo 9. It will mean 99 expo 9. Let me show you my work. 99 into expo 9 ohm. That's the maximum resistance you can represent with this color coding. Let me check the marking scheme. And he says brown and green and red and 9.9 expo 10. 99 into 10.9 or 9.9 expo 10 ohm. This is the maximum resistance you can. If all the 3 colors of white, then it will mean 9. The first white means 9, second white means 9, and the third 9 means if you use the third band also white, it will mean 10 raised to power 9. So 99 multiplied 10 raised to power 9. In the standard form, it can be written as 9.9 expo 10 ohm. So hopefully you have understood. The first color of the band represents a number. The second color represents a number. And the third color represents exponent of the 10. First color is representing a number. The second color is representing a number. The third color is representing the power or the exponent of the 10. Okay. The next question, it says in a 15 ohm resistor on the electronic circuit board has a correct power rating of 0.25 watt. The power rating of that resistor, 15 ohm resistor, is 0.25 watt. This much power it can bear. State a disadvantage of using a different 1500 ohm resistor with a power rating. That is, the meaning of the question is that if I use a resistor whose resistance is 1500 but its power rating is less than 0.25 watt. So when you will put this in the circuit is providing the voltage and the current this according to 0.25 watt, but you have put a resistor there whose power rating is less than 0.25 watt. So what will happen due to when the current flows through the resistor, it converts it into heat. So because its power rating is less than what the power is produced by that current and voltage in that circuit, so what will happen, that resistor will become hot. It might become very hot. It might become so hot that that resistor might glow. So that's if you use there a power, because there the power is supposed to be 0.25 watt. If you put a resistor there whose power is less than 0. Power rating is less than 0.25 watt, that resistor will blow or it will become very hot. And the second question is much greater than the 0.25 watt. If you put a resistor there whose power rating is more than 0.25 watt, it's a very electronic based question. And you see, if the resistors which will be of the 15 ohm but their power rating will be larger, normally what happens when the power when you increase the power rating of the resistor, their dimensions increases. You see that their length, width, height, that increases. The dimension or the size of the physical size of the resistor becomes larger. When the physical size of the resistor will be larger, so on you see on the board, on the circuit board, we have a certain space to put the resistor, to install the resistor on the motherboard, or I'm saying motherboard, circuit board. We have a certain space available to attach that resistor. So when you use resistors whose power rating is more than 0.25 watts, and I told you, when the power rating is increased, the length, width, and height, the dimensions of the resistor, or the size of the resistor, the physical size, length, width, height, that increases. So it's possible that that resistor might not fit in that slot. That resistor might not fit in that slot which you have on the circuit board. So that will happen when you will trying to use 15 ohm resistor whose power rating is more than 0.25 watt. So I have written this answer. Let me show you my answers, and here we go. Resistor will overheat and it might melt. This is this is what will happen if you use a resistor or less than 0.25 watt. And the second answer is for the when you use a resistor whose power is more than 0.25 watt. Dimensions of higher power resistors are larger. So high power resistors might not fit in the given slot on the circuit board. I hope that you have understood what I'm talking about. So let's check the marking scheme. What the marking scheme says, very simple question. So if you use less than 0.25 watt, so the answer says likely to burn out or blow or become too. And when you use a resistor whose power rating is more than 0.25 watt, likely to be larger in size. Likely to be larger means dimensions, length, width, height. It might not fit in the slot on the circuit board. So let's move to the next question. He says, figure, this is, I think, where we have. So we are on the question number 10, it's B part. Figure 10.3 shows part of a circuit that includes a variable resistor R and a battery of EMF 9 volt. State one similarity and one difference between electromotive force and the potential difference. So similarity between the EMF and the potential difference, electromotive force and the potential difference, is that they both have the same unit. They both are measured in joules per coulomb. Or for both of them, we use the unit volt. V-O-L-T, volt. For both of them, the unit can be joules per coulomb or the unit can be volt. That's the similarity between them. The difference between them is the EMF is always the voltage across the terminals of a source, and the potential difference is the voltage across the terminals of a appliance or a resistor or a component in the circuit. Another difference can be the electromotive force. Is the amount of energy which is converted. It involves the chemical energy being converted into the electric energy. But when you define the potential difference, then the electric energy is converted into any other form of energy. So that is the difference between the voltage and the potential difference and the electromotive force or EMF. I have written this answer. Let me show you my answer. Similarity between both of them. You see the similarity between both of them. EMF and the PD both have same unit, that is joules per coulomb or V. And the difference between them is EMF involves conversion of the chemical energy into the electric energy. Potential difference involves electric energy conversion into any other form of energy. Another difference can be that the EMF is the voltage across the terminals of a source of electricity, and the potential difference is the voltage across a resistor or a component in the circuit. So let's check the marking scheme, what the marking scheme says about this. She says that both, it's I think 3-mark question, both involve energy and charge measured in joules per coulomb, volts by voltmeter. Energy change is from other form except chemical to electrical in EMF. Energy changes from electrical to other forms except heat, light in potential difference. Or EMF is property of source and the potential difference is the property of part of the circuit. So I hope that you are able to state or describe the one similarity and one difference between the EMF and the voltage, potential difference. A light emitting diode is connected between the point X and Y so that emits light on the figure 10.3. Draw the symbol of the LED light emitting diode connected between the point X and Y. So you see, this is that circuit, and in that circuit, in this space X and Y, you have to draw an electric symbol for the LED. I have written this answer. Let me show you my answer. So on your screen, you can see I have drawn a LED symbol. It's a diode, and we make arrows of light coming out of it. So that represents a light emitting diode, LED. Hopefully, you have understood this. So let's move to the next question. He says the resistance of the R is increased. State what happens to the potential difference across the LED and the current in the LED. You see, when you will increase he says the resistance of the R is increased. If the resistance of the R is increased, it will take larger amount of voltage. So the LED will be getting less voltage. So if you put a voltmeter across the LED, it will show a lower reading. So the voltage across the LED will decrease. If the resistance of this R variable resistor will increase, it will start taking larger amount of the voltage from the battery. Only 9 volts are coming. So if the variable resistor will take larger amount of the voltage, the LED will be receiving less amount of voltage. So the voltage value or the reading on the voltmeter will decrease. Another thing which he asked is, how about the current? The current coming from the battery, because they both are connected in the series, if the resistance of the R will increase, the resistance of the whole circuit will increase. So the current coming from the battery will decrease. If the resistance of the circuit becomes higher, the current coming from the battery will become lower because they are connected in series. So whatever the current is coming from the battery, the same amount of current is flowing through both of them. So whatever the current is coming out of this battery, the same current flows through the variable resistor, and the same current will be flowing through the LED. Because when you increase the resistance of this variable resistor, the total resistance of the circuit will increase. So when the total resistance of the circuit will increase, the current coming from the battery will decrease. So the current flowing through the LED will decrease. So he was asking you two questions. He was asking you what will happen to the potential difference across the LED and what will happen to the current. The potential difference across the LED will decrease and the amount of current passing through the LED will also decrease. It's a 1 mark question. I have written this answer also. I think I have written the potential difference across the LED will decrease and the current through the LED will decrease. That is very simple. You just have to, here in this question, you only have to state. You don't have to explain. The LED is marked maximum current of 25 milliampere and the potential difference is 1.7 volt. Calculate the minimum value of the resistance R. So I know how much current is passing through the LED and I also know how much is the voltage drop across the LED. So very easily I can find out the resistance of the LED. If I know the voltage drop across the LED, if I know the current flowing through the LED, I can find the resistance of the LED. Okay, another the one actual question is what is the resistance of the variable resistor? So if you know the voltage drop here from the battery 9 volt came, if I know 1.7 voltage was taken by this LED, so I can tell how much voltage is taken by the variable resistor from 9 minus 1.7. So I will know how much is the voltage taken by this variable resistor, and the current which is flowing through the LED is 25 milliampere, and the same current will be flowing through this variable resistor. Now I know the voltage drop across the variable resistor and I also know the current flowing through the variable resistor because the LED and the variable resistor, they both are connected in series with each other. So whatever current is coming out of the battery, the same current is flowing through the variable resistor and same current is flowing through the LED. He said through the LED 25 milliampere current is flowing. So it means through the through the variable resistor, the 25 milliamperes, the same current is flowing through the variable resistor. So 25 milliampere current is flowing through the variable resistor. And from the battery, 9 volt are coming. So 1.7 volt are taken by the LED. So for the 9 minus 1.7, and the remaining voltage will be for the variable resistor. Now, if you know the voltage drop across the variable resistor and you know the resistance of the, if you know the, sorry, the current flowing through the variable resistor, using V equals to IR, I will, V equals to IR, R will be equals to V divided by I. You will be able to tell the resistance of the variable resistor. So let me show you my work. I tried to explain to you that how this is done. You see, LED 1.7 volt and the current through the LED is 25 milliampere. 25 milli means 25 into 10 power minus 3 ampere. So the voltage across the resistor R will be from the battery 9 volt are coming and 1.7 volt is taken by the LED. So for the voltage for the variable resistor or R will be 7.3, 9 minus 1.7, and the answer will be 7.3 volt. And the same current which is flowing through the LED, the same current will be flowing through the variable resistor also. So that will be the current flowing through the variable resistor R will be 25 milliampere, which means 25 x put minus 3 ampere. So use the formula V is equals to IR, R will be equals to V divided by I. So the voltage drop across the variable resistor is 7.3 volt and the current flowing through the variable resistor R is 25 x power minus 3. Just put these values in the calculator. 7.3 divided 2.5 x power minus 3 equals to, and you will get 292 ohm. 292 ohm. I hope you have understood that how I have calculated the resistance of the variable resistor. Let me check the marking scheme also. So it says 292 ohm will be the right answer. I hope you will be able to do this. It's a very good numerical. 292 ohm is the final answer. So have a good look at the marking scheme. So we are done with the question number 10. Let's go to the next question. Now, the next question on your screen, let me increase the size so you can see it. Sorry. We are doing May, June 2011 2-1 paper. In this video, we are attempting only the section B of this paper. We have done question number 9, question number 10, and now we are going to attempt question number 11. An atom of one isotope of sodium contains 11 protons, 13 neutrons, and 11 electrons. State the nucleon number, mass number of this isotope. You know that nucleon number of an atom is equal to the proton number plus the number of neutrons. So we have 11 protons, 13 neutrons. Just add them up and the answer will be 24. So the nucleon number will be 24. Let me show you my work. Okay. So on your screen, you can see the nucleon number is equals to the proton number plus the neutron. So 11 plus 13, 24. That will be the nucleon number. Let's check the marking scheme. What the marking scheme says, question number 11, A part, you can see 24 is the answer. The next part is a 1-mark question. He says, explain why the number of protons is equal to the number of electrons in a neutral. Whenever you have a neutral atom, you see the protons and electrons, they have opposite charge on them, and the amount of charge is same. So they have the protons and electrons. Protons have positive charge, electrons have negative charge. Proton and electrons have equal size of charge on them, but their signs are opposite. They have opposite charge on them of the equal size. So for an atom to be neutral, it's important that whatever is the amount of positive charge in it, it should have equal amount of negative charge. So in a neutral atom, the number of electrons and number of protons are supposed to be same. So let me show you my answer. I have written this answer also on your screen. This answer is showing now, I hope. So proton and electrons have opposite charge and magnitude of charge is same. For neutral atom, their numbers should be equal. Then the overall charge on the atom will be neutral because the positive charge of the protons will be cancelled by the negative charge of the electrons. And the charge will be present there, but the overall charge will be no charge, neutral. So let's check the marking scheme. What the marking scheme says, charges of electron and protons cancel. Protons and electrons have the same size of charge, but opposite in sign. So it's a 2-mark question. By looking at the marking scheme and by looking at the answer I have written, I hope that you will be able to write these answers. So let's move to the next question. The next question is, a nucleus of this isotope undergoes radioactive decay by the emission of a beta particle. State the energy changes that occur during the radioactive decay. So when a radioactive decay happens, the nucleus breaks, a beta particle is given out. So the nuclear energy, remember my words, what I am saying, nuclear energy will be converted into the the kinetic energy of the beta particles, and there might be some heat produced and there might be some light produced. So basically the nuclear energy will be converted into the kinetic energy. So it's a textbook answer. Don't forget this. So I have written answer, nuclear energy of the atom converts into the kinetic energy of the beta particle. But the marking schemes, he says the nuclear at the start or nucleus loses energy to the kinetic energy, electromagnetic energy, condone, light and photon. Condone means accepted. Condone, let me check. I have little, I think the condone means condone mean to accept. Yeah, accept. Sorry, I got doubtful what the meaning of condone. Okay, so the next question on your screen, we have, this is the question number 11B, second part. He says complete the nuclear equation that represents the decay by filling in the appropriate number in the blank spaces. Sodium is the chemical symbol for sodium. So we already know that the, there were we just calculated in another part that the nucleon number will be 24. So on the top of this sodium, I will write 24. And here a beta emission is happening. Remember my words that whenever a beta particle is given out, whenever a beta particle is given out, the daughter nucleus, its proton number will increase by 1 as compared to the parent nucleus, and its mass number or nucleon number will remain unchanged. So whatever, for example, here the magnesium is the daughter nucleus. So when a beta particle is given out by the sodium, the magnesium, which is the daughter nucleus, its proton number will increase by 1 as compared to the parent nucleus, and its mass number will remain the same. So the mass number of the sodium was 24. So the mass number of the magnesium will be also 24. The proton number of the sodium is 11, which is the parent nucleus, and the daughter nucleus with its proton number will be one more. So its proton number will be 12. On the beta particle here at the bottom we write -1, and on the top we write 0. I written this on a paper. You can see this is showing on your screen, this equation. So on the top of the sodium, I have written 24. Beta on the top, I will write 0, bottom -1. And magnesium in the bottom, I will write 12. On the top, I will write 24. So remember, when a beta particle is given out, the daughter nucleus proton number increases by 1, and its mass number do not change. Its mass number is equal to the mass number of the parent nucleus, but its proton number is one more as compared to the proton number of the parent nucleus. That's what happens when a beta particle is given out. So let's check the marking scheme, what the marking scheme says. And so marking scheme is on your screen. Hopefully you can see this. Our answers are right. So we are going to the next question. The next question is, he says, so you can see the whole thing. At the start of an experiment, the count rate due to a sample of this isotope of sodium is found to be 1200 counts per minute. This is shown in the figure 11.1 by a point plotted at the time t is equal to 0. The half-life of this isotope is 15 hours. On the figure 11.1, draw a smooth line to show how the count rate is expected to change between t equals to 0 and t is equal to 30 hours. So remember these wordings. The half-life is how much? 15 hours. So, when the time is 0, this is 1200. So after 15 hours, this 1200 will become half. So it will become, I think here, 600. And when another 15 hours will pass by, 600 will further become half, and it will become 300. So I will put mark at 15 comma 600, and I will put across at 30 comma 300, and then I will join them with the smooth curve. So let me show you my work. I've done this on a paper, so you can see here on the screen, and that after and at the start the count rate was 1200. So when one half life, which is of 15 hours, will have passed, so this count rate will drop to half. So 1200 divided by 2, it will be 600. So at 15 comma 600 I will put across, and then another half life of 15 hours will pass, and that 600 will further half, and it will become 300. So 30 comma 300, I'll put a mark there. Then I will join these 3 points with the smooth curve. So hopefully you have understood, and let's move to the next part. He says, explain why reading taken in an actual experiment may not follow a smooth line. In actual practice, when actual practice, if you will be taking actual count rates in actual practice, the points, if you join them, that will not be a smooth curve. The reason is that the emission of the radiation is a random process. You can never predict that when and how much radiation will be given out. It's a random process. That's why in the actual experiment, the line will be not that smooth, or the curve will be not that smooth. I've written this answer also. Let me show you my answer. And here on your screen, you can see this answer, that emission of radiation is a random process. Remember, this emission of radiation is a random process. So let's check the marking scheme. What the marking scheme says, you can see first part which we have drawn, line of decreasing gradient, not if it cuts the time axis of it. So 60 at 15 hours and 300 at 30 hours. So join them with the line with the gradient. I mean, draw a smooth curve. I have drawn that curve with the mouse of the computer, so that curve is not that smooth. But you will be drawing with a pencil, so that curve should be very smooth. Emission is a random, not predictable, not regular, and experimental error, he said. Okay, so hopefully you are understanding this. He says determine the count rate due to this isotope 30 hours before the start of this experiment. You can put a star on this part. This 1 mark question is not easy. Normally, what happens? He will ask you what will be the count rate after 30 hours. So 30 hours means 2 half-lives. So if now the count rate is 1200, so if for 15 hours will pass, it will become 600, and another 15 hours will pass, and it will become 300. But the question is very tricky. He's not asking you how much is the count rate after. No, he's asking how much is the count rate from this reference point 30 hours before that. Let me show you how I work on this, and I have done this the way normally I work with the half-life questions. So the 0 day, it is 1200. Normally the questions are, what is the reading after 30 days? So after 30 days, 15 days, 600, it becomes half, 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 half. So another half-life will pass, it will come. But the question is not this. The question is, what is the reading 30 days before? 30 days before. So, okay. So we will 1200, 30, 15 days before, it will be 24, double of this. It will be double of this, 2400. And 30 days, another half-life go back, and it will be double of the 2400. It will be 4800 counts per minute. So I think I use the word days. I think in the question he's not using the word days. He's using the word hours. So I by mistake wrote here days. Use the word hours. He's using the word hours. So I misunderstood and I wrote it days here. You can write 15 hours, 30 hours, 15 hours, 30 hours, 0 hours, 45 hours. Okay. So 30 hours before this reading was taken, the count rate will be double, again double. So you understand this how confusing. So the answer is 4800. He's not asking a normal question, a direct, straightforward question. He's making a trick in this part. So let's check what is the reading. Okay, 4800 counts, and so the next question he's asking is, in the space below, draw a label diagram of the apparatus used to measure the count rate of the radioactive isotope. Okay. So you see, if you want to draw the diagram of, I can show you. Let me go to the Google and I will show you a very famous diagram of the GM tube. I'm bringing GM tube, GM tube diagram. So you can draw this diagram. You see, this is that famous diagram. Let me copy it from here. Copy the image. And let's put it here and see. It. So let me explain it there and that, there and there and there. I hope that this is visible to you. So I can show you this diagram if this is visible. So by chance, what happened that I have not chosen you. Okay, so here you can draw this one. You see here we have central electrode that is positive, gas at low pressure. This is the mica window. This is the casing, and it's also acts like electrode also. And this is the supply, and here's the to the counting. So you can draw this diagram very easy. Let me increase the size so it becomes more and more clear to you. That to see this clearly. Just draw this diagram. This is the GM tube, Geiger Muller tube, Geiger Muller tube, GM tube. So you can draw this diagram. So, my dear students, we have reached the end of this paper, and today, and we have today, we have done this paper. This is May June 2011, 2-1 paper. And in this session, we have only attempted the section B of this paper. In the section B, we have done question number 9, question number 10, question number 11. And I have tried my best to explain you the concepts. And today we have worked very quickly, and so that the video should become of the shorter time duration. My dear students, if this video is helpful to you, if this video is helping you in your paper practice and improving your physics concepts, kindly like my YouTube channel, kindly subscribe to my YouTube channel, and also this recommend these videos to your other class fellows. You see, they are very helpful if you are at your home, you are not going to school, you are not going to your tuitions. So what happens at your home? You can play these videos on YouTube, and I will recommend that you use a big TV, like the big LEDs, and attach your computer with that LED and watch these videos on that LED. And you should have a hard copy of this paper and write the answers. And don't write the answer which I wrote. I wrote an answer. I described the answer, and then I also read what is the marking scheme. So write what you think is the best answer, and hopefully your writing skills and your answering skills will improve, and your grades will improve. So I'm trying my best. You should be so that you should grow, and you excel in the physics, and you get good grades in physics also. So everyone, I think that it's enough for today. So everybody, thank you very much. It was a pleasure teaching you. So thank you very much, everybody, and have a good day, and God bless you all.